When you examine modern network topologies, two of the most common devices you'll find in that topology are Ethernet switches and routers. That's our focus in this course. First, we'll learn how an Ethernet switch makes its frame forwarding decisions, and I'll demonstrate the configuration of several switch features. Then we'll examine routing, learning how a router makes its packet forwarding decisions. Also, we'll discover how a router gets its routing table populated. And since Ethernet switches and routers are so common in modern corporate networks, it is critical that you understand the theory of how they operate and how to configure some of their more common features. In this course, we have two primary topics, switching and routing. First, we'll consider Ethernet switching. Perhaps the most common network infrastructure device out there today is an Ethernet switch. For example, we'll use an Ethernet switch to connect out to our networked devices such as PCs, printers, servers, wireless access points, and more. And in our discussion of Ethernet switches, we'll cover both the theory and configuration of several features found on a Cisco Catalyst switch. Next, we'll examine routing, and we'll learn how a router decides where to forward a packet based on that packet's destination IP address. We'll see that a router's routing table can be statically configured, or we could use a dynamic routing protocol. We'll even do a side-by-side comparison of several of those dynamic routing protocols, and I'll show you how to configure one of them to route both IPv4 and IPv6 networks. And while it's great if you happen to have access to physical gear to practice on, that's not your only option. In fact, in our next video, I'm going to show you a few different options for getting your hands dirty with Cisco gear. I'll see you in that video in just a moment. While this course will primarily be covering theory, in some of the videos I'll be demonstrating commands on Cisco gear like routers and switches. And while you can certainly look over my shoulder as I enter those commands and learn that way, many students benefit from entering those commands themselves. So in this video, let's discuss 3 ways for you to get hands-on experience. First, you could use real gear. You could buy it used or refurbished from a variety of online sites, or maybe with your employer's permission, you might be able to use some extra gear from your workplace to set up a practice lab. Another option is for you to use a free application from Cisco called Cisco Packet Tracer. And after you download it, you'll be asked to log in, and you can use an existing Google account or create a free Cisco Networking Academy account. And this free application is a network simulator. That's as opposed to an emulator. Specifically, a simulator makes it feel like you're configuring actual Cisco gear, while an emulator is running the same operating system called Cisco Internetwork Operating System, or iOS, that you would find on physical equipment. So with Cisco Packet Tracer, you might not have all the features that you would have with physical gear or an emulator, but it is a fantastic piece of software, and it's more than sufficient for your CCNA studies. And a third option is to use Cisco Modeling Labs, or CML. While Cisco Packet Tracer was a simulator, CML is an emulator running real Cisco iOS. And at the time of this recording, you can purchase a year of access to the personal version of CML for around $200. And if you'd really like to use CML because it's an emulator, but you don't want to pay the nearly $200 annual fee for it, there is another option. What I'm referring to is Cisco's DevNet Sandbox, which is an online portal that lets you work with a ton of different Cisco devices to get an incredible amount of hands-on experience for free. Here's how it works. You go to devnetsandbox.cisco.com and you log in with an existing account, like a Google or Facebook account, or you could create your own free Cisco account. Then you can reserve a pod of gear at a certain date and time for a certain duration. And at the time of this recording, one of those equipment pods gives you access to free Cisco Modeling Labs, and you can reserve it for a 4-hour block of time. And there are plenty of online resources that you can search for step-by-step instructions on accessing and working with Cisco Packet Tracer, Cisco Modeling Labs, or Cisco's DevNet Sandbox. My recommendation is, since you're just getting started with Cisco networking, I'd go with Cisco Packet Tracer because it's a lot more simple to get up and going as opposed to finding the right console cables for real gear or getting connected through a VPN and going to Cisco's DevNet Sandbox, and it's free. However, any of the options we've discussed in this video should give you a great hands-on learning experience. In this video, we want to define a MAC address, a media access control address. And this is a 48-bit address that we say is burned into a network interface card. And the reason we say it's burned into a network interface card is when the manufacturer creates that card, they assign, as part of the hardware of that card, a unique MAC address. Now let's compare a MAC address with some of the other addresses that we might have in a network. A MAC address is 48 bits in length. Compare that to an IP version 4 address, which is 32 bits in length, and an IP version 6 address, which is 128 bits in length. And a big distinction between these addresses, other than their length, is that the MAC address is going to be used by a layer 2 device, like an Ethernet switch, to make forwarding decisions, while IP addresses are used by layer 3 devices like routers to make forwarding decisions. And when the manufacturer of a network interface card assigns a MAC address to a network interface card, that MAC address is divided into two distinct parts. The first 24 bits of those 48 bits are assigned to that vendor. Sometimes you'll hear this called a vendor code or an OUI, an organizationally unique identifier. So let's say that we have a vendor X that's going to be making these network interface cards. Well, that vendor is going to use the same first 24 bits on all of the network interface cards that they create. Then the vendor can select the last 24 bits to be assigned to those different network interface cards, but the first 24 bits, those are assigned to that vendor. And when you see a MAC address written, you might see it in a couple of different formats. You might see it with a colon delimiter, where we have a couple of hexadecimal digits and a colon and a couple of hexadecimal digits and a colon for a grand total of 12 hexadecimal digits. Remember that a hexadecimal digit can be represented with 4 bits, meaning that if I have 12 hexadecimal digits, 4 bits each, that gives me the 48 bits that we have in a MAC address. Alternately, we might see a MAC address written with a dot delimiter, where we have 4 hexadecimal digits and a dot, and 4 hexadecimal digits and a dot, and 4 more hexadecimal digits. However, regardless of the delimiter being used, remember that the first half of that MAC address is unique to the vendor. It's an OUI, an organizationally unique identifier, also known as a vendor code. In this video, we want to consider how an Ethernet switch can use a MAC address to make a frame forwarding decision. When we first power on a switch, it does not know where any MAC addresses reside. It has an empty MAC address table like we see here. But as traffic starts to flow through that switch, it's going to become educated about which MAC address lives where, and it's going to populate its MAC address table that it can then use to make intelligent frame forwarding decisions. Let's go through a scenario. Let's say that PC1 wants to communicate with the printer. When PC1 sends a frame into the switch destined for the printer's MAC address of the all-C's MAC address, the switch has no idea where the all-C's MAC address lives. So in order to get that traffic to its intended destination, the switch is going to do something called flooding. Flooding is when a switch sends a copy of a frame out all interfaces other than the interface on which that frame was received. But before we flood that traffic out, the switch just learned something. When that frame came in from PC1, and PC1 has the all A's MAC address, the switch realized that the all A's MAC address lives off of interface gig 1, and it makes a note of that in its MAC address table. Then, as we said, to get to the intended destination of all C's, which we have not learned yet, the switch then floods the traffic out all other interfaces. And it does make it to the printer. Unfortunately, a copy also makes it to PC2 and the server. They look at those frames, they say, that's not for me, and they discard those frames. The printer, however, says this is for me, and it's going to respond to the PC. When the printer responds to the PC, it sends a frame into the switch with a source MAC address of all C's, which tells the switch that the all C's MAC address lives off of port 3, and the switch adds that to its MAC address table. And this frame is destined for PC1, the all A's MAC address. And good news, the switch has already learned where the all A's MAC address lives when PC1 sent that initial frame into the switch. That means that the switch does not need to flood that traffic out. It knows exactly where the all A's MAC address lives. It lives off of gig 1, and it sends the frame just out of gig 1. Let's take a look at another scenario. Let's say that PC2 wants to communicate with the server, and at this point, the switch has not learned where PC2 lives, it has not learned where the server lives, but it's about to learn those things. PC2 sends a frame into the switch, which tells the switch that the all B's MAC address of PC2, it lives off of gig 2, and the switch makes a note of that. The switch does not yet know where the all D's MAC address lives, so what does it do? That's right, it's going to flood that frame at all other interfaces other than the interface on which that frame was received. It was received on gig 2, meaning that the switch is going to flood that frame out all other interfaces, which does get to the server. When the server responds with the all D's MAC address, the switch learns that the all D's MAC address lives off of interface gig 4. It makes a note of that, and it knows where the all B's MAC address lives. It's off gig 2, so we don't flood the traffic. We send the traffic directly to PC2. And at this point, the switch has a fully populated MAC address table, meaning that any device can talk to any other device without having its traffic flooded out to anyone else. That allows our switch to make intelligent layer 2 frame forwarding decisions based on MAC addresses. We know that an Ethernet switch is going to be able to use a MAC address to make an intelligent frame forwarding decision. But to better understand the operation of an Ethernet switch, let's take a look field by field at the format of an Ethernet frame. And we're going to begin with 8 bytes that aren't technically layer 2 bytes. These occur down at layer 1, the physical layer. It begins with a preamble of 7 bytes. This is going to send an announcement to say, here comes a data frame. Then there's another byte to say, and the data frame begins now. This SFD field, 1 byte in length, signals the end of the preamble and says, here comes the layer 2 data frame right now. And that's followed by the destination MAC address, the MAC address that an Ethernet switch is going to use to make an intelligent forwarding decision. And notice we say that it's 6 bytes in length. Remember, a byte has 8 bits. 6 times 8, that's our 48-bit destination MAC address. And we want to see where this frame came from. That's the source MAC address, also 6 bytes in length. And the switch is going to be looking at those source MAC addresses as frames come into the switch to populate its MAC address table. Next up is the length or type field, and in some cases, this is going to contain the number of bytes in the encapsulated packet. Other times, it's going to contain an indication of the network protocol that's been encapsulated, and that's normally going to be IP version 4 or IP version 6. And IP version 4 and IP version 6, they're going to encapsulate data inside of a packet. And normally that packet has a maximum length of 1500 bytes. That's going to comprise our payload. It has to be at least 46 bytes in length, and if it's not, our equipment is going to add padding so that it's at least 46 bytes in length. And then the Ethernet frame ends with an FCS, a frame check sequence. That's going to do a mathematical check to make sure that our data has not been corrupted in transit. And this is the format of a typical Ethernet frame. Remember, the preamble and the start field delimiter, they're technically happening at layer 1. So let me ask you this question. How much overhead is being added with an Ethernet header? This is an important number to know. Take a look at the diagram. What do you think? Well, the answer is 18 bytes. We have 6 bytes from the destination MAC address, 6 bytes from the source MAC address, 2 bytes from the length or type field, and 4 more bytes from the frame check sequence. So oftentimes you hear that the maximum transmission unit of an Ethernet packet is 1500 bytes, like we see here, but the maximum transmission unit of an Ethernet frame is 1518 bytes. Because a frame is a layer 2 entity and it adds on this 18 byte layer 2 header. And interestingly, in some equipment, we may be able to have a bigger payload. Instead of having a maximum of 1500 bytes, we might have equipment that supports something called an Ethernet jumbo frame. With a jumbo frame, the payload can be as big as 9,000 bytes. And that value can vary vendor to vendor, but typically it's about 9,000 bytes max. And if we think about it, this is going to give us more efficient transmission of data. We're sending more data with less overhead. Specifically with a traditional Ethernet frame, we had to send 18 bytes of layer 2 header for every 1500 bytes of data. Well, now we're using those same 18 bytes of header to send as much as 9,000 bytes of data. And that's a look at the format of an Ethernet frame, both a traditional Ethernet frame and the more efficient Ethernet jumbo frame. In this video, we want to define a term, and that term is VLAN or virtual LAN. And you could think of a VLAN as being analogous to a broadcast domain. That's an area of the network throughout which a broadcast is going to be propagated. Or we could think of that as a subnet, which is also another way to say a broadcast domain. But normally when we use the term VLAN, it's in reference to an Ethernet switch. Specifically, in an Ethernet switch, by default, all ports belong to the same broadcast domain or the same VLAN, probably VLAN 1 by default, meaning that a broadcast sent in one port is going to be replicated at all other ports. And that might be fine, but let's say that we had a wiring closet on the floor of a building, and on that floor we had a couple of departments, and we wanted to keep traffic from those two departments separate. A broadcast seen in one department should not be seen in the other department, and vice versa. Let's say in this example, we've got PC1 and server 1 and PC2 and server 2, and PC1 and server 1, they belong to the sales department. PC2 and server 2, they're part of the engineering department. And if we want to keep traffic isolated between sales and engineering, we could assign the switch ports to which PC1 and server 1 are connected. We could assign those to VLAN 10. We'll call that the sales VLAN, and they have their own subnet, 172.16.1.0/24. And if PC1 wants to communicate with server 1, it can do that. And PC2 and server 2, they're in the engineering VLAN. That's a separate broadcast domain with a separate subnet of 192.168.1.0/24. And PC2 can communicate directly with server 2. However, devices in the sales VLAN cannot communicate with devices in the engineering VLAN because they're in different subnets. If this is truly a layer 2 Ethernet switch, then the only way we're going to be able to get traffic from one VLAN to another VLAN is to connect to an external router. Now, sometimes we have a multi-layer Ethernet switch, which can do routing, but if this is really a layer 2 switch, we need to connect to an external router to get traffic from one VLAN to the other. Let's say that PC1 has a legitimate reason to talk to server 2. We're going to have to route to do that. And here's the way it works. A router is going to be connected using a special type of connection called a trunk. A trunk has the unique ability to carry traffic for multiple VLANs. So if PC1 wanted to communicate with server 2, and these devices are on different subnets, we're going to have to route between those subnets. PC1 is going to send traffic to router R1 over that trunk, and that trunk port on router R1, it's going to be logically divided up into different sub-interfaces. One sub-interface is going to be in the sales VLAN, and one sub-interface is going to be in the engineering VLAN. That's going to allow PC1 to send traffic down to the router, and that router is going to route traffic back up over that same trunk link into the engineering VLAN of which server 2 is a member. And that's a look at how we can take the physical ports on a layer 2 Ethernet switch and logically divide them up into different subnets or different broadcast domains, which we called VLANs. Now that we understand the theory of VLANs, in this video we're going to set up a couple of VLANs. We'll begin by creating VLAN 10. It's going to be for the sales department, so we'll give it a name of sales. We'll create VLAN 20, and that's going to be for the engineering department. And after we create these VLANs, we're going to notice that by default, they're empty. In other words, they don't have any ports in them. So we're going to populate these VLANs with ports on our switch. And I'm going to be doing this demonstration on a physical switch. It's a Cisco Catalyst 3750 series switch, and it has a series of fast Ethernet ports. We're going to take the first 12 of those ports and put them into VLAN 10. The next 12 ports, they'll go into VLAN 20, and then we'll verify our VLAN configuration. Now, let's go out to a live interface and set this up. Here on switch SW1, let's take a look at the VLANs we have by default. We can do that with a show VLAN command, and we see that currently all of our ports belong to the default VLAN of 1. And if I scroll on through the output, we see there's a lot of extra information here, and honestly, we don't really need that information these days. It has to do with transparent mode bridging, which is a token ring concept, and we see that we've got some token ring and FDDI reserved VLANs. We can largely ignore all of that. So instead of seeing all this information, I prefer to say show VLAN brief instead of just show VLAN. This is going to give us a more concise view. We still see these extra token ring and FDDI VLANs that we can ignore, but we don't have to see all of that extra output at the bottom of the screen. So again, show VLAN brief. I prefer that over show VLAN. But we still see that all ports belong to our default VLAN of 1. Let's create a couple of new VLANs. To do that, we'll go into global configuration mode, and I'll say VLAN 10, and we'll give it a name of sales. Let's create VLAN 20. I'll give it a name of engineering. Let's go back out to privilege mode and verify the creation of our VLANs. I'll say end and show VLAN brief again. And now we see that we do have a sales VLAN number 10 and an engineering VLAN number 20, but notice that they don't have any ports assigned to them. Let's populate these two VLANs. We'll go back into global configuration mode, and I want to put the first 12 fast Ethernet ports into VLAN 10, and I could do that by going into interface configuration mode for fast Ethernet 1/0/1 and say, you belong to VLAN 10, and then go into fast Ethernet 1/0/2 and say, you belong to VLAN 10, but that would take a while to go through all of the ports. We can use a shortcut, and it's called interface range configuration mode. Specifically, I can specify a range of interfaces, and any command I give applies to every interface in that range. To do that, I'll say interface range fast Ethernet 1/0/1-12. Notice that I'm now in interface range configuration mode, and any command I give applies to interfaces fast Ethernet 1/0/1 all the way through fast Ethernet 1/0/12. And I'm just going to give one command for these ports. I want to say that they belong to VLAN 10. To do that, we say switch port access VLAN 10. And by the way, an access port is a port that belongs to one and only one VLAN. That's as opposed to something we'll talk about later called a trunk port. But now we'll say that these 12 ports belong to VLAN 10. Let's go into interface range configuration mode for fast Ethernet 1/0/13 through 1/0/24. And we'll say switch port access VLAN 20. And we're done. Let's end. And once again, I'll say show VLAN brief. And great news, we now have our VLANs populated. The sales VLAN has our first 12 ports, and the engineering VLAN has the next 12 fast Ethernet ports. And that's a look at how we can go into a Cisco Catalyst switch, create VLANs, populate those VLANs, and then verify the VLANs. In this video, we want to consider a special type of connection called a trunk connection. We understand the concept of VLANs at this point, and notice that these two switches have a couple of VLANs. There's a sales VLAN and an engineering VLAN. And let's say the sales PC needs to talk to the sales server connected to the bottom switch, and the engineering PC needs to connect to the engineering server on the bottom switch. And the question is, how do we interconnect those switches such that we can communicate using more than one VLAN? One option would be to connect a sales VLAN port on the top switch to a sales VLAN port on the bottom switch, and the same thing for the engineering VLAN, but that's not going to scale very well. Instead, we can create a special type of connection called an Ethernet trunk. And an Ethernet trunk has the unique ability of carrying traffic for more than one VLAN. That means that the sales traffic and the engineering traffic, that can all flow over this single connection. And as the traffic goes, for example, from the sales PC down to the sales server, the Ethernet trunk can tag the sales traffic to say, you belong to the sales VLAN, and the same thing for the engineering traffic. And when we're setting this up on a Cisco Catalyst switch, you may have two different options for the trunk encapsulation type. One is an older Cisco proprietary approach called ISL, inter-switch link. I want you to know that it exists because sometimes that is the default, but today we almost always want to use the industry standard of IEEE 802.1q, often referred to as simply .1q. And with a .1q trunk, the way an Ethernet frame is identified as belonging to a particular VLAN is we add 4 bytes to that layer 2 header. and one of the fields inside of those 4 bytes say that you belong to this specific VLAN. There is one exception to that, however. There's a special VLAN called the native VLAN. That is the one and only one VLAN on an Ethernet trunk that does not get tagged. Let's say that the sales VLAN in this example was the native VLAN. In that case, when sales traffic went over that Ethernet trunk, it would not have those 4 bytes added. Which begs the question, how does the bottom switch know what VLAN that frame belongs to? And the answer is, the switches need to agree on who the native VLAN is. It's VLAN 1 by default. For security purposes, it's recommended that you use a different native VLAN, but you should make sure your switches agree on who the native VLAN is. That way, when a switch receives an untagged frame, it knows where to send it. So again, a native VLAN that's on a .1Q trunk, not on an ISL trunk, and it does not have any tag bytes added. And that's a look at how we can send traffic for multiple VLANs over a single connection using an Ethernet trunk. In this video, we want to see how to configure an Ethernet trunk. Specifically, we're going to be using the .1Q trunk encapsulation type, and we have 2 links in our topology, and we'll set up trunking on both of those links. And then after we're done, we'll verify the trunk creation. Now, let's go out to a live interface and set this up. Well, let's begin our configuration on switch SW1. I'll go into global configuration mode, and I'll say interface range, using that shortcut, gigabit 0/1-2. And by the way, the switches I'm using right now are not physical switches. They are emulated switches. I'm using CML, Cisco Modeling Labs. And I'll go into interface range configuration mode for these 2 interfaces on switch SW1, connecting down to switches SW2 and SW3. And I'll say, I want to use the .1Q trunk encapsulation type with the command switch port trunk encapsulation .1Q. And I'll say I want these to be trunk ports with the command switch port mode trunk. And we're done on SW1. Let's go over to SW2, and we'll say for interface gigabit 0/1, the only interface that switch SW2 is using, I want it also to use the .1Q trunk encapsulation type with the command switch port trunk encapsulation .1Q. And we want it to be in trunk mode with the command switch port mode trunk. We'll give a similar configuration on SW3 for interface gig 0/1. We also want it to use the .1Q trunk encapsulation. So we say switch port trunk encapsulation .1Q. And let's make it a trunk port with the command switch port mode trunk. And we're done. Let's go verify our configuration back on switch SW1 with the command show interfaces trunk. And this is going to show us any trunking interfaces. And great news, we're trunking on ports gig 0/1 and 0/2. We see that we're using .1Q encapsulation for both ports, and they have the default native VLAN of 1. And that's a look at how we can go into a Cisco Catalyst switch, specify the trunk encapsulation type, tell a port to be a trunking port as opposed to an access port, and then verify our trunk configuration. Let's imagine that we have a couple of routers, R1 and R2, and they're connected with redundant connections, meaning that if one connection goes down, the other connection can take over. But maybe there's some sort of an issue with the way we have routing set up, and we find ourselves in a routing loop, where traffic is going from R1 to R2 and back to R1 and so on, just endlessly circulating. Well, the great news with a router is a packet will not endlessly circulate, because a router is going to assign a time to live value or a TTL value to a packet, and every time it goes into another router, that value is going to be reduced by 1 until it eventually reaches 0. If a TTL value reaches 0 for a packet, a router is going to discard that packet. Let's say that right now, as a packet comes out of R1, it has a TTL, or a time to live value, of a 2. It goes into R2, which decrements it by 1, giving it a time to live value of a 1. It goes back to R1, which decrements it by 1 again, resulting in a TTL value of a 0. And R1 then drops that packet, so we don't have this endless loop. Unfortunately, we don't have the luxury of a TTL value with a switch. With a switch, it is possible that a frame will endlessly circulate when we have a topological loop like we see here. Imagine that we had a broadcast that a switch is sending out. Remember that a switch is going to flood a broadcast out of all ports other than the port on which it was received. Well, if we have a broadcast that's endlessly circulating through a layer 2 loop like this, we have a broadcast storm, and that's going to impact all the devices connected to these network segments. PCs are going to grind to a halt. You're not going to be able to move the mouse on the screen because they're so busy looking at all those broadcast frames. And that's the challenge that we need to overcome. We want redundancy. We want to have physically a looped topology. So if one connection goes down, another connection can take over. But logically, we don't want a loop. We want to logically have a loop-free topology, and that's what we get with a protocol called Spanning Tree Protocol, or STP. And think of a spanning tree as being analogous to a real tree. Here's a tree in my backyard, and you'll notice that as we come up from the root of the tree, the branches go off in different directions. One branch never loops back onto another branch. That's the logical topology that we want to construct. We want to have a loop-free topology in the form of a tree in our network. Physically, we can have loops for redundancy's sake, but logically, we don't want loops, meaning that we're not going to be sending traffic over some of those links to prevent those loops. That's what Spanning Tree Protocol is going to do for us. Way back in the mid-1980s, Radia Perlman was working for DEC, Digital Equipment Corporation, and working for DEC, she developed something called STP, the Spanning Tree Protocol, which allows us to have redundant connections while still logically giving us a loop-free topology, and that's what we'll probably be using on our Ethernet switches today. But back in the mid-1980s when Radia Perlman invented this, there were no Ethernet switches. Instead, we had Ethernet bridges, and we'll talk in just a moment about the distinction between a bridge and a switch. But I want you to know that a few years after Radia Perlman developed this, the IEEE came out in 1990 with a standards-based version of Radia Perlman's Spanning Tree Protocol, and that standard is IEEE 802.1d. Now, let's consider the distinction between a bridge and a switch. They both logically work about the same way. They both make forwarding decisions based on destination MAC addresses seen in frames. However, a bridge makes those decisions in software, which is a lot slower than a switch, which has dedicated hardware in the switch that can make these decisions at line rate without any noticeable delay at all. And as a result of the slowness of a bridge doing all this in software, we typically only had a couple of ports on a bridge, where we might have a 48-port switch as an example. A bridge back in the 1980s and early 1990s, that was typically used to interconnect a couple of collision domains so that one collision domain didn't get too big. But now we can have a switch with dozens and dozens of ports. And the reason I'm taking time to bring up a legacy device like a bridge is that since Spanning Tree Protocol was invented in the 1980s, when there were only bridges and not switches, the term bridge is still used in Spanning Tree Protocol. So later in this chapter, when we talk about something like a root bridge or a bridge ID, realize that that root bridge, as an example, is referring to a root switch. We just still use that original terminology of bridge. At this point, we understand STP or Spanning Tree Protocol is going to give us a physically redundant topology. So if one link goes down, another link can take over, but we know it's going to give us a loop-free logical topology where traffic is not going to circulate endlessly. But in order for that to happen, we have to have one or more ports not forwarding frames. And what we're going to do in this video is take a sample topology like the one we see here and identify the roles played by the different switches and the different ports. Specifically, we have 4 questions that we want to ask as we're analyzing a spanning tree topology. Number 1, who is the root bridge? And we'll define that in a moment. Who are the root ports is question number 2. Thirdly, who are the designated ports? And finally, whoever's left, those are going to be the blocking or the non-designated ports. But let's begin by considering the root bridge. This is going to be the switch in the topology that other switches are pointing back to in this loop-free logical topology that looks sort of like a tree because it doesn't loop back on itself. And we'll see later in this chapter how we can go in and make a switch the root bridge. Depending on our traffic patterns, we might want to select a particular switch. But here, we're just going to analyze this existing topology. And it's going to be the switch with the lowest bridge ID. The bridge ID is made up of 2 parts, a priority and the MAC address of the switch. The priority defaults to 32.768, and that's going to be the default for all the switches we see here, meaning that the tiebreaker is going to be the MAC address. Who has the lowest MAC address in this topology? It's SW1 with the all ones MAC address. Question number 2 is, who are the root ports? And a root port is the one and only one port on a non-root bridge that's closest to the root bridge in terms of cost. So this is going to be on a non-root bridge. SW2 and SW3, they're each going to have one root port. But what do we mean by cost? Well, cost is a function of speed. And traditionally, we've used a table like this called the short path cost method, where a gig port has a cost of 4, and a 10 gig port would have a cost of 2, and a 100 meg link has a cost of 19. But as we start to get into faster and faster link speeds, like 40 gig or even 400 gig speeds that we might find in a data center, this traditional approach isn't going to work because we're not able to distinguish between those higher speeds. So in the future, you're probably going to be using the long path cost method. Here, we take 20 terabits per second, divide by the port speed, and that's your cost. So a 1 gig link would have a cost of $20,000. But here we'll use what you'll find by default on most switches, and that's the short path cost method. Let's focus first on SW2. How can it get to the root with the lowest cost? If it goes out of port gig 0/1, that's going to be a cost of 4 because we're going out over 1 gig link to get back to the root bridge. What if I go out of gig 0/2 over to SW3? Well, that's a cost of 4 to get to SW3. And then I go from SW3 up to the root bridge. That's another cost of 4, so it's 4 plus 4. That will be a total cost of 8. What is my least cost on SW2? Yeah, it's going to be the gig 0/1 port. So gig 0/1, that is my root port. And by the same token, with SW3, it's a cost of 8 if I go to SW2 and then up to SW1, as compared to a cost of just 4 if I go directly to SW1. So on SW3, gig 0/1, that is my root port. And the third question we ask is, who are the designated ports? And every segment is going to have one and only one designated port, and that's the port on the segment that's closest to the root in terms of cost. The great news, we have a shortcut here, and that is we know the designated port for every segment going into the root bridge is going to be on the root bridge, because you don't get closer to the root bridge than being on the root bridge. So for switch SW1, gig 0/1 and gig 0/2, those are our designated ports for those two segments. However, what about that segment between SW2 and SW3? If I'm on the SW2 side of that link, and I'm sitting on switch SW2, it's a cost of 4 to get to the root. But the challenge is, it's also a cost of 4 if I'm on SW3. Which end of this segment, going between SW2 and SW3, do I use? It's a tie. Well, a tiebreaker is going to be to look at each end of that segment, and whichever end is connected to a switch with the lowest bridge ID, that's the winner. And SW2 has a lower bridge ID because it has a lower MAC address than SW3, so the designated port for that bottom segment, that's going to be on SW2. And finally, we ask, who's left? Assuming a port is not administratively shut down, it's going to be blocking if we haven't already identified it. And in this case, the only port that's left is gig 0/2 on SW3. That's going to be our blocking or non-designated port. And that's a way we can analyze an existing spanning tree topology, determine who is the root bridge, who are the root ports, who are the designated ports, and who are the blocking ports, which are not going to be forwarding frames. It's those blocking ports that allows us to have this logical loop-free topology. In this video, we want to get some practice identifying the port states of a spanning tree topology. And you might remember there are 4 questions we ask. We ask, number 1, who is the root bridge? Then we identify the root ports, the designated ports, and then the blocking ports. To begin with, let's ask, who is the root bridge? And I encourage you to take a look at this topology and determine who is the root bridge based on the priorities and MAC addresses provided. And if you need to, feel free to pause the video while you figure out who the root bridge is. But in this case, the root bridge is SW1. Notice that SW1 and SW2 have lower priorities than SW3 and 4. Their priorities are 16/384. So it's going to be either SW1 or SW2, but since the priorities are a tie between those two switches, we go with the lowest MAC address. And SW1 begins with 000 as opposed to 001 on SW2. So SW1 has the lowest bridge ID, and it is our root bridge. Next, we ask who are the root ports. And a root port is a port on a non-root bridge that's closest to the root in terms of cost. Let's begin on switch SW2 and consider each of its 3 ports. The TE1/0/1 port, that's a 10 gig Ethernet port. That has a cost of 2. Gig ports have a cost of 4. So if I go directly out of TE1/0/1, that's a cost of 2. If I go out of gig 1/0/7, it costs me 4 to go down to SW3 over that gig link, and another cost of 4 to go from SW3 up to the root over another gig link. 4 plus 4, that's a cost of 8. What if I go out of gig 1/0/5? That goes down to SW4. It cost me 4 to get there over the gig link, and then it cost another 4 to go from SW4 up to SW1, our root. 4 plus 4, that's 8. So clearly on SW2, the root port, the port with the least cost to get back to the root bridge, is TE1/0/1. What about SW4? Well, if it goes directly to SW1 over that gig link, that's a cost of 4. It could go up to SW2. It's going to cost 4 to get there, though, and then it would cost an additional 2 to go from SW2 to SW1. That's a total of 6. That means on switch SW4, our root port is gig 1/0/1. Next, consider SW3. If I went out over gig 1/0/2, that's a cost of 4 to get up to SW2, then an additional 2 to get from SW2 back to SW1. That's a cost of 6 in total. Now we have a bit of an issue. We have a tie as we exit gig 1/0/10 and 1/0/11. They each have a cost of 4 to get up to the root bridge. So which one do we use? Well, normally in a situation like this, the tiebreaker is going to be to look at the far end of each link, and whichever far end switch has the lowest bridge ID, that's the port we're going to use. However, in this case, the far end switch is SW1 for both ports. We have another tie. And the next tiebreaker is often misunderstood. Many people have heard that in the event of a tie, we're going to go with the lowest port ID, which is true, but many people misvisualize this, which is why I crossed the links in this topology. Many people look at this and say, oh, I'm going to go with the lowest port ID. That's gig 1/0/10 on SW3. But it's not the port ID on the local switch. It's the lowest port ID on the far end switch. And the lowest port ID on the far end switch into which we're connecting is gig 1/0/3, and that connects to gig 1/0/11 on switch SW3, so that is going to be our root port. Next up, we ask who are the designated ports, and we know that every segment has one and only one designated port, and it's the port in that link closest to the root in terms of cost. And we get to take a big shortcut here because we don't get closer to the root than being on the root, meaning that all the links connecting into the root are going to have their designated port on the root bridge. But what about the link between SW2 and SW3? Well, I put myself on each end of the link and say, which end has the lowest cost? If I'm on the switch 2 end of that link, the cost is 2. I just go over that 10 gig link to get back to the root. If I'm on SW3, though, I've got to go over a gig link to get back to the root. Which end is the lowest cost? The end on SW2. That means for that segment, gig 1/0/7 on SW2, that's the designated port. And similarly, for the link between SW2 and SW4, if I'm on the SW2 side, it's a cost of 2 to get to the root. If I'm on the SW4 side, it's a cost of 4. So gig 1/0/5 on SW2, that's my designated port for that segment. And at this point, we've addressed all of our links, and there are some ports that are not labeled. Well, those are going to be our blocking ports. So gig 1/0/10 on SW3, gig 1/0/2 on SW3, and gig 1/0/2 on SW4, they're not root ports, they're not designated ports. Therefore, as long as they're administratively up, they are blocking or non-designated ports. And that's a review of how to take a look at a topology and identify spanning tree protocol port states. We know that spanning tree protocol is going to allow us to physically have a redundant topology while giving us a logical loop-free topology, and it does that by blocking one or more ports in the topology. In this example, switch SW3 is blocking on port gig 0/2, and that blocking port can transition to a forwarding state if the root port on SW3 were to go down. The question we want to answer in this video is, how long does that take? Well, first we need to understand that SW3 is periodically receiving messages from SW1. They're called Bridge Protocol Data Units, BPDUs, to say, hey, I'm still alive. But let's say that link goes down between SW1, our root, and SW3. Suddenly that link is broken. Does switch SW3 immediately say, I need to take this blocking port and make it a forwarding port? No, it wants to give time for switch SW1 to send a BPDU into gig 0/1. It's going to wait for 20 seconds, and during this time, gig 0/2 is still in the blocking state. After 20 seconds have elapsed, and we've heard no BPDU from our root bridge, then the switch says, it looks like something is up with gig 0/1. I need to start transitioning gig 0/2 to the forwarding state. And it goes into another state. It goes into the listening state, and it stays there for 15 seconds. During the listening state, switch SW3 is listening to BPDUs coming in, all of its different ports. It's taking a look at everyone's bridge ID. It's comparing it to its own bridge ID. Who knows? Maybe switch SW3 is now the root because the root has gone down. It's trying to learn its place in the network, and it does that for 15 seconds. After 15 seconds, it then goes into the learning state. And when it's learning, it's populating its MAC address table. A MAC address available off of gig 0/1 before might now be available off of gig 0/2. And it's going to remain in that learning state for 15 seconds, after which it will finally transition to the forwarding state, and gig 0/2 will become the root port of SW3, and it can send traffic to the root via SW2. But grand total, that took 50 seconds to transition from blocking to forwarding. And that's the default times that we have with traditional spanning tree protocol, IEEE 802.1d. Well, we're going to see later in this chapter that there's a variant of spanning tree protocol called rapid spanning tree protocol, which can converge much more rapidly than 50 seconds. In this video, let's consider some different versions of spanning tree protocol. Let's go back first to the original industry standard. That was IEEE 802.1d that came out in 1990. And with this version of spanning tree, we say that it is a CST, a common spanning tree, meaning that if I have several VLANs flowing on trunk connections between these switches, all those VLANs will be using the same spanning tree topology. They all see the same switch as their root bridge. That might not be optimal though. Here, let's pretend we have 4 VLANs, VLANs 1, 2, 3, and 4, and we only have one instance of spanning tree topology. They all share this one instance where SW1 is the root. That might be fine for, let's say, VLANs 1 and 3, but perhaps VLAN 2 would benefit from having SW2 as its root, just based on traffic flow, and maybe VLAN 4 would benefit from having SW3 as its root based on traffic flow. Well, we don't have that flexibility with the traditional common spanning tree, but Cisco gave us an enhancement called per VLAN spanning tree that does give us that flexibility. Per VLAN spanning tree, or PVST for short, allows each VLAN to have its own instance of spanning tree protocol. Here we still have those 4 VLANs, but now they're each running in their own instance. Again, VLANs 1 and 3, they benefit from having SW1 as their root. VLAN 2 benefits from having SW2 as its root. VLAN 4 benefits from having SW3 as its root. And with PVST, we can have that. And in the literature, you might see PVST sometimes written as PVST plus. Let me make that distinction for you. Technically, if you see PVST plus, that means these switches are interconnected via .1Q trunks. If you just see PVST, it means they're not connected via .1Q trunks. But typically, they are going to be connected using .1Q trunks. Just be aware in some of the literature, you might still see that referred to as PVST. But let's consider scalability with PVST. What if I had 1,000 VLANs? Do I really need to have 1,000 instances of spanning tree protocol? I may not even have 1,000 switches. It seems a little bit inefficient. And many, many years ago, when switches were not as powerful as they are today, that could be an issue, having too many instances of spanning tree protocol running. And a fix for that was multiple spanning tree protocol, or MSTP. Here, every VLAN still gets an optimal tree, but we don't have to have a tree per VLAN. And this is a standard. It's IEEE 802.1s. And here we define spanning tree protocol instances. Here I've got two instances, and I'm saying VLANs 1 and 2, they would benefit from having SW1 as their root, so they're assigned to that instance that has SW1 as the root. VLANs 3 and 4, they would benefit from having SW2 as the root, and they're assigned to the instance that has SW2 as the root bridge. You see, the benefit here is I don't have to have an instance of spanning tree running on my switch for every single VLAN, because some VLANs benefit from having the same topology as other VLANs. So this allows us to reduce the number of instances running on a switch while still giving every VLAN an optimal tree. And like I was saying, this overcomes an issue we had many years ago when our switches did not have the processing power that they do today. But today, personally, I'm not overly concerned with multiple instances of spanning tree bogging down my switch. I'm perfectly fine with PVST. However, I would prefer a faster version of PVST, and that's Rapid PVST. Rapid PVST is Cisco's enhancement to the IEEE 802.1W standard. That's going to help us converge much quicker than 50 seconds that we discussed earlier. In fact, depending on how the failure happens, the convergence time might be anywhere between a few milliseconds to about 6 seconds at a maximum. So personally, if I'm using a modern day Cisco Catalyst switch, this is my go-to version of spanning tree protocol. I'm not concerned about multiple instances running. I do love the fact that it gives me an optimal tree for every VLAN, and I'm a big fan of the short convergence time. Now that we understand the theory of spanning tree protocol, in this video we want to set it up. Specifically, we're going to see a topology and we'll determine who the root bridge is and what are the port states. Then we're going to go in and make a specific switch in the topology, the root bridge, and we'll verify that change took effect. And to speed things up just a bit, we'll configure Rapid PVST on our switches so we get fast convergence while still giving every VLAN an optimal spanning tree. Now let's go out to the live interface and set this up. All right, take a look at the topology on screen, and you might want to pause the video and determine who do you think the root bridge is. Well, everybody has the default priority of 32.768, so we look to see who has the lowest MAC address. And in this case, it's SW1. That's going to give SW1 the lowest bridge ID. And on SW1, if I say show spanning-tree, it tells me very clearly that this bridge is the root. And we see that we've got a priority of 32.768. And here is our MAC address. And that's the same MAC address that we have for the root because we are the root. Now, something that might be not obvious here is this priority statement that says 32.769. I thought it was 32.768. What's going on here? Well, the way Cisco implements this is they do something called an extended system ID, where this priority number is the actual priority of 32.768 plus the VLAN number. Here we're dealing with VLAN 1. So this 32.769, it's simply 32.768 plus the VLAN number. And the reason they do that is to minimize the use of MAC addresses by making sure that every VLAN has a unique bridge ID. But we're on the root right now, so it's no surprise that both of our ports, gig 0/1 and 0/2, they're designated ports because a designated port is the port on a segment that's closest to the root, and we don't get closer to the root than being on the root. Let's go over to SW2 and see what's going on there. We'll do a show spanning-tree. Here we see our root port is gig 0/1, and we're forwarding, but notice that we're in a blocking state on the other two ports. These two ports are connecting us over to SW3. Remember that every link has one and only one designated port, but it's not us on SW2. When we're trying to determine who that designated port is, we say which end of a segment is closest to the root in terms of cost, but in this case, SW2 and SW3, they're equally close to the root. So the tiebreaker is which one of those switches has the lowest bridge ID. And in this case, if you look at the topology, you'll see that switch SW3 has a lower MAC address. That gives it the lowest bridge ID, and the ports on the SW3 side of these two links, they're going to be designated. In fact, let's verify that. Let's go over to SW3 and do a show spanning-tree. And we'll see that for gig 0/2 and 0/3, we are designated ports on SW3, and we're forwarding. These are all gig ports, so they each have a cost of 4. But let's say for traffic flow reasons for VLAN 1, it would be best if SW3 were the route instead of SW1. Here's how we can administratively configure the route bridge in a topology. Let's go into global configuration mode, and on SW3, I'm going to say spanning-tree for VLAN 1. I want this to be the primary route. So I say route primary. We'll press enter, and let's see what happened. Let's do a show spanning-tree command again, and now it says that we are the route. And the reason we're the route is when I said spanning-tree VLAN 1 route primary, it took this priority from 32.768 down to 24.576. In other words, we reduced 32.768 by 25%. And that makes us the route bridge. And finally, let's see how to convert these switches to running rapid PVST Plus so we can enjoy much faster convergence times. To do that, we can go into global configuration mode, and I'll say spanning-tree mode. We've got 3 options: the multiple spanning tree mode, PVST, or what we want, rapid PVST. We'll enter that. We'll confirm the change with a show spanning-tree command again. And it says that we're enabled for rapid spanning tree protocol. And we want to make sure that all the switches agree on that. So I'll go over to SW2 and say spanning-tree mode, rapid PVST. And we'll finish it up on SW1 by saying spanning-tree mode, rapid PVST. And that's a look at how we can verify the route bridge and port states in a topology, influence who the route bridge is, and then change the spanning tree protocol mode to rapid PVST. In this video, we want to consider a feature that Cisco calls EtherChannel, or you might hear it more generically referred to as link aggregation. The idea is this: we want to have multiple links interconnecting our switches, and Spanning Tree would take a look at that and block traffic over all but one of those links. But what we can do with an EtherChannel is logically bundle together multiple links into what looks like a single connection. That's going to allow us to simultaneously send traffic over all links in this EtherChannel bundle. And as a result, we're going to get increased bandwidth. We're going to be able to load balance across those links. We're going to be able to have redundancy. So if a link were to fail, we can still send traffic over any remaining links. Now here, I just have 2 links in this bundle, and the bundle is represented with that oval superimposed over those links. But we could have 2 links in a bundle, 4 links, or a maximum of 8 links. And those links, when we're configuring them, can be set up dynamically using a protocol such as PAGP, which is Cisco proprietary. That's the port aggregation protocol, or LACP. That's an industry standard, the link aggregation control protocol. Now let's take a look first of all at how Cisco's PAGP works. The idea is we may be able to go to just one switch and set up an ether channel by negotiating the formation of an ether channel with the other switch. First of all, let's consider the ether channel port mode of ON. ON technically is not using PAGP, or LACP for that matter. It's not sending PAGP frames. It's not going to respond to PAGP frames. It's just ON. And if you want to set up an ether channel and one side has its ether channel port mode set to ON, the other side had better be set to ON as well. That's the only way it's going to work with ON. So you cannot have one side set to auto and one side set to ON, or one side set to desirable and the other side set to ON. That's not going to work. Also, you cannot have both sides set to auto. Auto says I'm willing to become an ether channel, but I first have to receive a PAGP frame. I'm not going to suggest that we form an ether channel. And with both sides set to auto, even though both sides are willing, nobody initiates the formation of a channel and one is never formed. However, if one side is set to auto and the other side is set to desirable, that will form an ether channel, because the ether channel port state of desirable will send out a PAGP frame asking the other side, hey, do you want to form an ether channel? And if the other side is auto, it will respond to that PAGP frame and say, yes, let's do it. Let's form an ether channel. And the ether channel will be brought up. And it will also come up if we have both sides set to desirable. They'll each see one another's PAGP frames, and they will mutually agree to bring up an ether channel. Now, this is PAGP. And the port states work exactly the same way with LACP, except instead of auto and desirable states, we have passive and active states with LACP. Passive takes the place of auto and active takes the place of desirable. And if you're working on non-Cisco gear, this is probably the protocol you're going to be using. And finally, I want to dispel a misconception that many people have with EtherChannel. Many people would take a look at a topology like this and assume that the first packet is going to go over the first link and the second packet would go over the second link and so on. That's not necessarily true, because EtherChannel is going to use a load balancing algorithm. It's going to use math to determine which link a particular frame goes over. And on many Cisco Catalyst switches, the default load balancing algorithm I've seen used is using the destination MAC address. Remember that a MAC address has 48 bits. Well, how many bits do we need to represent 4 different values? 1 value for each link. It just takes 2 bits to do that, doesn't it? 2 raised to the power of 2 is 4. So let's put those different bit combinations on those links. The top link gets 00, the next link gets 01, then 10, and the bottom link gets 11. And those are going to represent the last 2 binary bits in the MAC addresses of the destination. And let's say we're going to be sending traffic into this server farm. We have servers 1, 2, and 3. And as we're looking at their MAC addresses, the last hexadecimal digit in the MAC address for server 1 is a 1. The last hex digit in server 2's MAC address is a 5. And the last hex digit in server 3's MAC address is a D. They all seem different. However, if we look at those hex digits in binary, we see that the 2 rightmost binary bits are identical. They're 01, which corresponds to the second link in this Ether channel. That means if the PC is sending traffic to either server 1 or server 2 or server 3, it's always going to be using the same link to do that. It's always going to be using that link indicated with a 01. So we're not always getting perfect load balancing as we might assume. The good news is we don't have to stay with this default load balancing algorithm. We get to change. We get to select from these options. We could base our link selection on destination IP or MAC address, source IP or MAC address. Personally, I prefer to randomize things a bit by considering both source and destination addresses, either IP or MAC addresses. So I would choose one of the bottom 2, and that's going to add a bit of randomness. So if I had multiple PCs, they would potentially use different links to get over to those servers. And that's a look at how link aggregation works, a feature that Cisco calls EtherChannel. In this video, let's discuss the configuration of an Ether channel. And we're going to do this using the same topology that we used earlier for spanning tree protocol. And we want to create a 2-port Ether channel between a couple of switches in that topology. And we're going to use the PAGP, the port aggregation protocol approach to negotiating this Ether channel. And once we have the channel set up, we want to set up a .1Q trunk over the channel. After all, a trunk could really benefit from an Ether channel thanks to the increased throughput of an Ether channel and a trunk carrying traffic for multiple VLANs. So it's really common to configure an Ether channel to act as a trunk. And once we're done, we'll verify the Ether channel. Now let's go out to the live interface and set this up. We're going to be setting up our Ether channel between switches SW2 and SW3. And we're going to go into interface range configuration mode for the 2 ports in this Ether channel. Let's go into global configuration mode, and I'll say interface range gig 0/2-3. This is a time saver allowing me to configure both ports at the same time. And to create an Ether channel, I'm going to say channel-group, and I'm going to give it an identifier because we could have more than one Ether channel on a switch. I'll give it an identifier of a 1. And for the mode, I'm going to use PAGP, and I'm going to say desirable. I'm going to send PAGP frames to the far end. And if the ports at the far end have their Ether channel port modes set to either auto or desirable, this should bring up an Ether channel. And once we press enter, this creates a virtual port representing our Ether channel. It's port channel 1. Let's go into that interface that just got created. We'll say interface port-channel 1. And let's configure a trunk on this interface, which is a logical interface made up of those 2 physical interfaces. I'm going to say switch port trunk encapsulation .1Q because we don't want to use ISL. And then I'm going to say be a trunk with the command switch port mode trunk. And while we're here, let me show you how to set the load balancing algorithm. We're going to do that in global configuration mode. We'll say port-channel, load-balance, and we've got these options. I'm going to say I want to use a combination of the source and destination MAC addresses. And we'll enter that. And let's go give a complementary configuration on the far side. We'll go over to switch SW3, and just to make sure everything is set up here, I'll go into interface range configuration mode for gigabit 0/2-3, and I'll say channel-group 1 mode. I'll set this side to auto, so it will respond to PAGP frames being sent by SW2. This creates our port channel 1 interface. We'll exit. We'll go into that interface of port channel 1, and we'll set up a trunk on this port with the command switch port, trunk, encapsulation, .1Q, followed by switch port mode, trunk. And I'll set this to the same load balancing algorithm. In global configuration mode, I'll say port-channel, load-balance, source, destination, MAC. Let's see if it worked. Let's do a show IP interface brief command, and we see that we have this virtual interface called port channel 1. Great news. It is up at layer 1. It is up at layer 2. Let's do a show EtherChannel summary command, and we see information about this EtherChannel. We see it has an identifier of a 1. We're using PAGP. These are the 2 ports that are members of that channel. Do we have a trunk? Let's do a show interfaces trunk command, and it'll tell us if we have any trunks. And yes, indeed, we have a .1Q trunk running on port channel 1. And that's a look at how we can logically group together physical interfaces into one logical interface called an EtherChannel, set up a trunk over that EtherChannel, and adjust the load balancing algorithm. We know that an Ethernet switch is going to make a forwarding decision based on a layer 2 MAC address. Well, in this video, we're going to see how a router makes its forwarding decision using a layer 3 IP address. Specifically, in this example, the PC wants to get to the server. And after the PC first boots up, it's given its IP address, its subnet mask, its default gateway, and the source IP address for this communication to the server is going to be the PC's IP address, 192.168.1.2. The destination IP address is the server, 192.168.2.2. But in order for that PC to get off of its local subnet, it needs to send traffic to router R1. And to send a frame into R1, we know its IP address, 192.168.1.1, but to send a frame to R1, we need to know its MAC address. And right now, the PC does not know the MAC address of interface gig 1 on R1. So what it does is send out an ARP broadcast message. ARP stands for Address Resolution Protocol, and it's asking, hey, can somebody tell me the MAC address for this IP address of 192.168.1.1? And router R1 says, yes, that's me. I have the all ones MAC address. The PC gets that, and it makes a note of that in its ARP cache. So the next time it wants to go to 192.168.1.1, it doesn't have to send out an ARP broadcast. It's going to memorize the MAC address of that IP address. So now the PC, it's ready to send out its packet going to the server. The important thing to realize here is the source and destination IP addresses do not change. However, the MAC addresses do change. In the first leg of the journey, the source MAC address is the PC's MAC address of all A's, and the destination MAC address is interface gig 1 on R1. You see, both of those MAC addresses are on the same network segment. The source IP, that's the PC's IP address. The destination IP, that's the server's IP address. And again, those do not change throughout this communication flow. But now R1 looks at that destination IP address of 192.168.2.2, and it's going to take a look at its routing table to see if it knows how to get there. Great news. Router R1 does have an entry in its routing table for the 192.168.2.0/24 network. And it says, if you want to get to that network, you need to go to a next hop address of 10.1.1.2. And that's R2. This is how R1 can intelligently forward that traffic. It looks at the destination IP address checks its routing table for the most specific entry that will get it to that IP address, and in this case, it's going to forward it to the next hop of R2. Notice the MAC addresses have changed as we go from R1 to R2. Now the source MAC address is the All2's MAC address. That's the outgoing interface on R1. The destination MAC address of All3's, that's the incoming interface on R2. You see, every network segment, our MAC addresses are updated for the source and destination MACs on that segment. But now R2 is in possession of the packet. It takes a look at that destination IP address and it asks, can I get to 192.168.2.2? Well, in this case, R2 says, yes, I'm directly connected. I just need to send this out of interface gig 1, and it does. And that gets the packet up to the server. And in that last leg of the journey, as we're exiting R2 on gig 1, that gig 1 MAC address is our source MAC address for this segment, and the destination MAC address is finally the all B's MAC address of the server. But notice, at no point did the source or destination IP addresses change. It was just the MAC addresses that were updated for every network segment that we crossed. We know that a router is going to make a packet forwarding decision based on a destination IP address. And the question we want to begin to address in this video is, how does the router build its routing table that tells it how to forward traffic to that destination IP address? One way that we'll discuss later is to have a dynamic routing protocol, but in smaller networks, we might not need a routing protocol. We could just go in and administratively add routes to the router's routing table. In this example, we might go into router R1 and say, if you want to get to the 198.51.100.0/24 network, you need to go to a next hop IP address of 10.0.0.2, which is R2. And if you want to get to the 203.0.113.0/24 network, you need to go to a next hop IP address of 10.0.0.6. That's R3. And I mentioned that we could do static routing instead of running a dynamic routing protocol, but we could actually run these side by side. And the great news is the static routes that we administratively configure, by default, they're going to be more believable than a route learned via some routing protocol. And again, that static route is going to say, to get to this network, go to this next hop IP address. And there are times when we might want to use a default route. A default route says, if you don't have a specific route entry to get to a network, go this way. In fact, the default route is written as all zeros, which encompasses all possible IP addresses. And if there's not a more specific route entry in a routing table, we're going to take that default route as some people say, a gateway of last resort. We don't have a more specific way of getting to a destination, so let's use the default route. And there are times when we want to use default routes. Consider the topology on screen. We've got a branch office that only has one way out to the rest of the world, and that's to go to a next hop of the HQ router back at the headquarters. So if the PC over at the branch office, if it wants to reach any network within the headquarters, or if it wants to get to any network out on the internet, it's only got one way to go. The only possible way to get to those external networks is to go to a next hop address of 10.0.0.1, the HQ router. So instead of us going into BR1 and setting up a bunch of static route entries to get to all the individual networks within HQ, we could just have a default route to say, if you don't have a more specific route entry, come to me, come to HQ. And in a situation like that, we're going to be statically configuring that default route. But in a large enterprise, we might have a router sitting at the boundary of the intranet and the enterprise network. Well, that router could advertise via a dynamic routing protocol a default route to let all the other routers in the enterprise know to come towards it to get out to the internet. Now that we understand the theory of static and default routing, in this video we want to set them up. We'll begin by configuring a couple of static routes that will allow a PC to reach a couple of remote networks. We'll verify that static routing configuration in the router, and then we'll do a default route configuration, where we might have just one path to get out to the rest of the world. Now let's go out to the live interface and first configure static routing. We're sitting on router R1 in this topology you see on screen, and if we check our routing table right now with the show IP route command, you'll see that the only routes we know about are those that we're connected with. That's what the C indicates. It means we're directly connected. Now the L, that's an actual IP address of a local interface. Notice the /32 subnet mask. If you ever see a /32 subnet mask, that means we're talking about a single IP address. That tells us that 10.0.0.1 is the IP address assigned to interface gigabit 0/2 in this case. But we have not been educated about any non-directly attached networks. So let's see how to add a couple of static routes to router R1. We'll go into global configuration mode, and I'll say IP route, and we enter the network address that we want the router to put in its routing table. It's 198.51.100.0, and the subnet mask is 255.255.255.0. And now we say, what is the next hop IP address to get to this network? Well, in this case, we want to go to 10.0.0.2 to get to that network. That's the IP address of the incoming interface on router R2. Let's do one more. Let's say IP route 203.0.113.0. Again, we have a 24-bit subnet mask. 255.255.255.0. This time, R3 is going to be the next hop with an IP address of 10.0.0.6. And let's enter that. And we'll end that configuration. That's how easy it is to add a couple of static routes. Now let's confirm that those routes are indeed in our routing table. Let's do a show IP route once again. And this time we should see a couple of extra routes. And we see they're indicated with an S indicating a static route. And the final question is, can we reach IP addresses in those subnets? Let's try. Can I ping, for example, 198.51.100.1? Yes, I can. Can I ping 203.0.113.1? Yes, I can. So what we have been able to do here is to go into router R1 and tell it how to reach a couple of remote networks, not by running a dynamic routing protocol, but by pointing to a next hop IP address. Now let's take a look at another topology where we will configure a static default route. You'll see that we have a new topology on screen now. Let's go over to router BR1 and let's see what routes it knows about. We do a show IP route. And we do not know about any networks that are not directly attached. Now, if you look at that topology, you'll notice that if I want to get to any network outside of BR1, for example, I wanted to get to a network within the HQ site or a network out on the internet, I've only got one possible way to get there. And that's to go to HQ. That's an opportunity where I could use a default route, and I'm going to statically configure it. So let's go into global configuration mode, and I'm going to say IP route, and to specify a default route, both the network address and the subnet mask, they're all zeros. So I'll say I want to route to 0.0.0.0 space 0.0.0.0, and the next hop IP address is going to be the HQ router. That's the only way I can get to any other network that's not local to me. And that incoming interface has an IP address of 10.0.0.1. Let's take a look at what that route looks like. Let's do another show IP route. And as we saw earlier, a static route is indicated with an S, but we also have an asterisk. What that means is this is our candidate default route. If I'm trying to reach a network and I don't have a more specific entry in my routing table to get to that network, then I'm going to go to what is called my gateway of last resort, my default gateway, which in this case is 10.0.0.1. And to verify this works, let's see if I can ping the IP address on the internet side of the HQ router. Let's try to ping 203.0.113.1. Let's press enter, and that was successful. And that's a look at how we can go in and start to populate a router's routing table with static routes, and how we can add a default route which we can use to get to any network that is not otherwise specified in the IP routing table. Even though we could go into a router and add a bunch of static routes, that's not going to scale well for the enterprise. For medium to large size networks, we need a dynamic routing protocol typically. A dynamic routing protocol allows routers within the network to share information about known networks. And we have several to pick from. We see some of those listed here on screen. And a question that a network designer might ask is, which routing protocol should we use? Well, one consideration is scalability. How big can this thing get? RIP, as an example, the routing information protocol, is not very scalable. Specifically, if a network is available more than 15 routers away from us, it's not reachable with RIP. RIP considers anything more than 15 routers away to be infinitely far away, so that's not going to scale. OSPF is very scalable. I used to work down at Walt Disney World in Florida where we had about 600 routers, and we ran EIGRP. It was very scalable. ISIS also very scalable. We tend to see that in service provider or data center networks. Maybe the most scalable protocol of all is BGP, the Border Gateway Protocol. That's the protocol that runs the internet. It ties together the various internet service providers and different companies. In fact, it's typically used between autonomous systems. We don't use BGP that often within our network, and we'll keep our focus on routing within our network for now. Another consideration might be vendor interoperability. If we have routers that are all Cisco, like we did down at Walt Disney World, we might consider EIGRP, because for a long time, EIGRP was a Cisco proprietary protocol. Back around 2010, Cisco started to open that up a little bit to other vendors, but it didn't really catch on that much. Other vendors still don't have widespread adoption of EIGRP. So if you had some Cisco routers and maybe some Juniper routers, you might want to use something like OSPF instead of EIGRP. And sometimes it comes down to your IT staff. Are they more familiar with one routing protocol than another? There are a lot of features in these protocols, so if your IT staff is super knowledgeable about ISIS, that might be the deciding factor to cause your company to go to ISIS instead of OSPF. And another one is convergence time. If a failure occurs in the network, the great thing about a dynamic routing protocol is if there's another way to get to a destination network, we can route around that failed network segment. And that process of routing around a failed segment is called convergence. How quickly do these converge? Well, it varies. RIP, for example, is fairly slow. It could take up to 3 minutes to converge. OSPF, EIGRP, ISIS, they're very fast, maybe just a few milliseconds to just a few seconds. BGP is going to vary in its convergence time, but on the internet, because the internet is so big, it might take a few minutes to converge, but that's typically okay over the internet. But within an organization, RIP is usually going to be too long of a convergence time to be considered. And we're not forced to run just a single routing protocol. We could have multiple routing protocols running in the same network, which begs the question, what if we have conflicting route information? What if one protocol says, come to me to get to this network, and another routing protocol says, no, I'll get you to this network? Who do we believe? Well, the believability of route information is determined by something called the administrative distance. The lower the administrative distance of route information, the more believable it is. And we don't get more believable than being directly connected to a router. If a router has an interface and it's connected to a specific network, that is super believable, so its administrative distance is the minimum value of 0, which is the most believable. If we go to the trouble to administratively configure a static route, that's going to be believable, and it's going to have an administrative distance of a 1 by default. Next up is BGP, the Border Gateway Protocol. It seems to beat out all of the other dynamic routing protocols, but remember, we typically are not running BGP within our company. We're running it between our company and our internet service providers. EIGRP, that's the Enhanced Interior Gateway Routing Protocol. That has an AD or administrative distance of a 90. That's more believable than OSPF. Open shortest path first. That's a little bit more believable than intermediate system to intermediate system, ISIS, and that's more believable than the Routing Information Protocol, or RIP for short. That has an AD of 120. And this is not meant to be a comprehensive listing, but I did want you to get familiar with some of the common options for dynamic routing protocols and why we might choose one over another. In our previous video, we talked about BGP, the Border Gateway Protocol, as a protocol that would communicate between our company and our different ISPs, our internet service providers. Well, in an example like that, our company would have a number called an autonomous system value, an AS value. Each of our ISPs would have their own values as well. And we define an autonomous system as being a network under a single administrative control. And we'll talk in a moment about how BGP is going to primarily route between autonomous systems. Another term we need to understand is an IGP, an Interior Gateway Protocol. This is a protocol that is going to run within an autonomous system. such as RIP or OSPF or ISIS or EIGRP. And what runs between autonomous systems? We gave BGP as an example. That's an EGP, an exterior gateway protocol. So that's going to take us between one autonomous system and another autonomous system. In a case like this, Company A is autonomous system 65,000. One ISP is 65,100. Another ISP is 65,200. But within Company A, within that autonomous system, we're going to be running some sort of an IGP, an interior gateway protocol. And again, examples of those might be the Routing Information Protocol, or RIP, ISIS, that's intermediate system to intermediate system, OSPF, that's open shortest path first, and EIGRP, the Enhanced Interior Gateway Routing Protocol. And running between autonomous systems, we can have an EGP. And currently, the only exterior gateway protocol we have is BGP, the Border Gateway Protocol. And these different protocols fall into different categories: distance vector, link state, or path vector. First, consider RIP. RIP is a distance vector routing protocol. And if you think back to your high school math or science class, do you remember what a vector is? It gave us two pieces of information. It gave us magnitude and direction. In other words, how big is it and in which direction is it? Well, that's what RIP does. RIP is going to give us a vector that points to a network. The magnitude of that route is going to be how many router hops it is away. That's the metric used by RIP. If it can get to a network in a fewer number of hops one way versus another way, it's going to go with the route that has the fewest number of hops. And it's going to tell us in which direction to go to get to that network by specifying a next hop IP address. OSPF, however, and also ISIS, they fall under the category of link state. With link state, it's like having a map of the entire network. And this works just like your car's navigation system does. Your car's navigation system, or maybe an app on your smartphone, has a map of the world. And if you're trying to get from your current location to another location and you want to drive there, your car's navigation or that mapping application on your smartphone, it's going to assign a cost to different roadways. Higher speed roadways would have a lower cost. Back roads, gravel roads, they would have a higher cost. And it's going to perform a mathematical calculation using something called the Dijkstra algorithm to determine what's the lowest cost. And that's the path that it's going to choose. And both OSPF and ISIS, they run that very same Dijkstra algorithm on their map of the network stored in a link state database. But the thing I want you to know about a link state routing protocol for now is it has a map of the network. Now, EIGRP is also a distance vector routing protocol. It does not have a map of the network, so it is not link state. Many people would refer to this as an advanced distance vector routing protocol, and I would agree with that, because it does have very fast convergence compared to RIP. But in a category of its own is BGP, the Border Gateway Protocol. It's a path vector routing protocol. Vector implies that it tells us the next hop IP address to go to get to our destination network, but the path is something unique to BGP. It actually gives us a listing of every autonomous system that we have to cross through in order to get to that destination network. And that's an overview of interior gateway protocols that run within an autonomous system and our exterior gateway protocol of BGP that runs between autonomous systems and what category each routing protocol falls into. Is it distance vector, link state, or path vector? The routing protocol that we're going to be considering in this course is RIP, the Routing Information Protocol. And we're going to consider it in this introductory course because it's one of the simpler routing protocols out there. It is older. You probably will not find it in large enterprise networks, but you might see it in some smaller networks out there because it is so easy to configure, and there are 3 different versions we want to consider. RIP version 1, which we should definitely not be using today, RIP version 2, and RIPng, or RIP Next Generation. Let's consider each one of these, beginning with RIP version 1. With version 1, when a RIP speaking router sends out a network advertisement, it does it with a broadcast, which goes everywhere throughout a broadcast domain. That means that PCs and printers and all devices connected to a subnet are going to hear these broadcasts about routing updates. That's not very efficient. Also, version 1 does not support variable length subnet masking, and that means we cannot advertise a network, for example, with a /22 subnet mask. We have to send advertisements at a classful boundary, and that's not very efficient. Also, RIP version 1, it supports IP version 4 only. Things got a lot better with RIP version 2. Instead of sending out a broadcast to everybody on a subnet, RIP version 2 is going to send its route advertisements to a multicast address of 224.0.0.9, which is going to go only to RIP speaking routers. Version 2 does support variable length subnet masking, so we can advertise a subnet mask of any length, and version 2 adds authentication to prevent somebody from maybe maliciously adding a router to the network and corrupting a routing table. But like version 1, RIP version 2 only supports IP version 4. We can run version 2, however, concurrently with RIPng if we want to add support for IP version 6. Because RIPng or RIP Next Generation, it does support IP version 6, and it's going to send its route advertisements to an IPv6 multicast address of FF02::9. So if you wanted to support both IP versions 4 and 6, you might want to run RIP version 2 and RIPng on the same router. And the way RIP judges the best path to reach a network is based on hop count. It asks, how many routers do I have to hop over or transit in order to get to a destination network? That's the metric of RIP, hop count. In this example, if we're going from the network on the left to the network on the right, then we're hopping over or we're transiting two different routers. That's a hop count of 2. And RIP is limited in scalability because its maximum hop count is 15. If we have a hop count of 16 to reach a network, that's considered to be infinitely far away. And another characteristic of RIP I would want you to know about is how it sends out its updates. It sends both full updates and triggered updates. A full update is its complete routing table that it's going to send out every 30 seconds. That's a little bit chatty compared to some other routing protocols, and that doesn't scale very well with larger routing tables. But if something has happened to the topology of the network and route information is suddenly changed, RIP is not going to wait for that 30-second interval to send out the update. If something happens, it will send out a triggered update to let other RIP-speaking routers know that some network change has occurred. In this video, we want to consider a couple of features that RIP has: split horizon and poison reverse. Now, split horizon is a rule that's used not just by RIP, but also by EIGRP, and that rule says that if a router receives an advertisement for a network in a specific interface, that router will not advertise that same network out of the interface on which it was learned, and that can prevent a routing loop or what's called a count to infinity problem. Consider this example. Let's imagine that split horizon has been disabled, and R3 is connected to the 10.1.1.0/24 network, and we see in R3's routing table it's 0 hops away because it's directly connected. And it has advertised previously over to R2 that it's directly connected, and R2 knows that the 10.1.1.0/24 network is available to it if it just hops through or transits one router. So it has a hop count of 1 from the perspective of R2. But let's say something happens to that network. It goes down. When that happens, R3's routing table says, we're no longer directly connected. We're infinitely far away from this. But let's say that R2 then advertises to R3, I can reach 10.1.1.0/24 in one hop. And R3 says, oh, that is great news because I could not reach it previously. If you're 1 hop away and I go through you, that means I'm 2 hops away. Do you see the issue here? R2 is not 1 hop away from that network any longer because that network is down, and R3 has a false sense of assurance that it can reach that network. When R3 does advertise that network back to R2, saying it's 2 hops away, R2, since it learned the network from R3 in the beginning, it's going to update its hop count to say it's 3 hops away. And following that same logic, R2 advertises to R3 that it's 3 hops away. R3 says, I'm now 4 hops away. And this goes on until we reach a hop count of 16. Remember, when we get to a hop count of 16 in RIP, that network is considered to be infinitely far away. It's unreachable. This is a count to infinity problem, but by having split horizon enabled, as it is by default, router R2 is not going to advertise back to R3 any networks that it has learned from R3. That's going to prevent this count to infinity problem. Another way that RIP attempts to prevent a routing loop like this, or a count to infinity problem, is a feature called poison reverse. This says when a network goes down, a router is going to advertise a poisoned route, a route with an infinite metric, saying that this route is unreachable. Going back to our previous topology, let's once again say that the 10.1.1.0/24 network off of R3 goes down. R3's hop count to that network goes from 0 to infinity, But with poison reverse, it's going to send an advertisement over to R2 saying that the hop count to 10.1.1.0/24 is 16, which is infinitely far away. That's going to make R2 look at that advertisement, that poisoned route advertisement specifically, and say that network is infinitely far away. And that's a look at two features RIP uses to prevent a routing loop or a count to infinity problem, and those were split horizon and poison reverse. In this video, we want to configure RIP version 2. Specifically, we're going to have a 3-router topology, and we want to configure RIP version 2 on all routers to advertise all connected networks, and then we'll verify the reachability to those networks. Now, let's go out to the live interface and set this up. If you take a look at the topology, you see that we're dealing with 3 routers, and our goal is to configure RIP version 2 on all of these routers such that they can reach all networks in the topology. And we're going to begin on router R1. We'll go into global configuration mode. And to start the RIP routing process, we say router RIP. Now, unlike OSPF or EIGRP that you may have configured, there's no number after RIP. We're not specifying an autonomous system number or a process ID. We just say router RIP. I want to run version 2 of RIP, so I'll say version 2. And I've got a couple of networks to advertise. I want to advertise network 192.168.1.0, and we'll advertise network 192.0.2.0. We're done on R1. Let's move over to R2. On R2, a very similar set of commands. We'll say router RIP. Let's make sure we're running version 2 of RIP. A couple of networks to advertise here as well. 192.0.2.0. and network 203.0.113.0. One router to go. Let's go to router R3. We'll go into global configuration mode and say router RIP once again. Version 2. We don't want the broadcast behavior version 1. I've got a couple of networks to advertise here. I'll say network 203.0.113.0 and network 172.16.1.0, and we're done. We should now have full reachability throughout this network. We can verify that by checking out the IP routing table. We can view that with the command show IP route. And we see that we have learned 2 networks via RIP. The R indicates this is a RIP learned network. And I want you to notice for the 192.0.2.0 network, that's the network between R1 and R2. It says we're 1 hop away. For the 192.168.1.0 network, we would have to transit or hop over R2 and then R1 to get there. So it is 2 hops away. What does the 120 mean? Do you remember the discussion we had about administrative distance, the believability of a routing source? Well, 120, that's the administrative distance of RIP. And one final check, let's make sure that I can ping the gig 0/1 interface on R1. That will verify that we can cross this entire network. Let's do a ping to 192.168.1.1. Success. We have now configured and verified RIP version 2. In this video, we want to configure RIPng, or RIP Next Generation. This is going to allow us to route IP version 6 networks. We're going to use the same topology we used in our RIP version 2 demonstration, and we want to configure RIPng on all routers and verify reachability to all networks when we're done. Now, let's go out to the live interface and set this up. You'll notice our topology is identical to our RIP version 2 topology. In fact, these routers still have our RIP version 2 configurations on them. I can do a show IP route, and we can still see networks learned via RIP. But we see in this topology that we also have IP version 6 networks, and we're going to use RIPng to route those networks. And before we get into the configuration of RIPng itself, if we want to route IP version 6 networks on our router, we might have to go in and say IPv6 unicast routing to say that this router is enabled to route IP version 6 traffic. It might be disabled by default. So I'll give that command first, and then I'll create my RIPng routing process. And to do that, instead of saying router RIP, I say IPv6 router RIP. And one extra thing, I give a process name. With RIP version 2, we didn't give a process ID or an autonomous system number or anything. We just said router RIP. Here, we're able to have multiple instances of RIPng processes running, so I need to give it a name. And this name is locally significant. It does not have to match on a neighboring router, and I'll call it CCNA. and I go into RIP configuration mode. However, if I use context-sensitive help, you'll see that a command is conspicuously missing here. There's no network command like we used in RIP version 2. So how do I advertise networks? Well, the network command was really advertising networks to which we had interfaces attached, and those interfaces were up. So for RIPng, we go directly into the interface and we say, I want you to participate in RIPng, and I want to advertise the network to which you're connected. So let's go into our two interfaces. I'll go into interface gig 0/1, and to make this interface participate in the CCNA RIPng routing process, I say IPv6 RIP. I give the process name of CCNA, and I say enable. Let's do the same thing for interface gig 0/2. I'll just up arrow to retrieve that previous command, and we're done with our configuration on R1. Let's give a similar configuration on R2 and then on R3. On R2, in global configuration mode, I begin as we did before by enabling IPv6 routing. I'll say IPv6 router RIP. I give a name of CCNA, but that did not have to match. I'm just doing it so it keeps it straight in my mind. And once again, we'll go into our interfaces and say gig 0/1. And to make this interface participate in the CCNA RIPng routing process, I'll say IPv6 RIP CCNA enable. Let's do that for our other interface, gig 0/2. And we're done on R2. One router to go. On R3, we go into global configuration mode and once again say IPv6 unicast-routing. And to prove that the RIPng process name is locally significant, I'm going to give a different process name on this router. I'll say IPv6 router RIP. And instead of giving the process a name of CCNA, I'll give it CCIE. And we go into our two interfaces, interface gig 0/1, and we say IPv6 RIP for the process name of CCIE this time. Enable. Let's do the same thing for our other interface. We'll make it participate in the routing process. And we're done. Now we can see if we have reachability throughout the network. Instead of doing a show IP route, I can do a show IPv6 route. And we see from the R code that we have successfully learned a couple of networks. Another command we can give to learn more about our configuration is show IPv6 protocols. This is going to tell us the name of our routing process, CCIE, and it tells us the interfaces that are participating. If I want even more information about this RIP routing process, I could say show IPv6 RIP, and it's going to give me counter information. For example, it says I'm going to be sending my full update every 30 seconds, just like RIP versions 1 and 2, and those routes expire after 3 minutes. So we don't get quicker convergence with RIPng. It's still fairly slow. And we see that split horizon is currently on, poison reverse is currently off, and this is another way where we can see what interfaces are participating in the RIPng routing process. And that's a look at how to configure RIPng on top of an existing RIP version 2 configuration to add support for IPv6 routing. Congratulations on finishing this course. This course covered a collection of routing and switching topics. For example, we saw how to configure VLANs, trunks, spanning tree protocol, EtherChannel. We did that for switches, and we learned how those switches made their frame forwarding decisions. Then we turned our attention to routing. And after we examined how a router makes its packet forwarding decisions based on IP addresses, we discussed how a router's routing table gets populated. We could use static routes, maybe a dynamic routing protocol. In fact, we configured one dynamic routing protocol in this course. It was RIP, which is short for Routing Information Protocol. Now, if you're feeling good about what you've learned, I encourage you to keep that momentum going and join me in another course. Until then, I want to give you my sincere thanks for entrusting me with your time in this course. That's not something I take lightly. And also, since this course did cover so many technologies, if you need to go back and review some of them, that is perfectly okay. You can go back and rewatch whatever you would like to review. I wish you all the best in your studies.